We're going to be taking a look at a vector in this video. And so just to start you off here, what is a vector anyway? Well, a vector is both direction and magnitude. And we can use vectors to stand for a lot of things. The direction is important, of course. And this concept of magnitude, the magnitude, even though it's going to be a distance on the graph here, it can stand for a lot of things. It could be distance, it could be speed or velocity, it could be force, and a lot of other things. What do they look like? Well, let's draw one right now, and we're going to make this vector S. So I hope you can see this in the video. Let me scoot this over just a little bit. And I want you to do this precisely. One of the things with vectors is we need to make sure that we draw them as precisely as we can. As a matter of fact, it's tough to draw these sometimes precisely, so we tend to use a lot of algebra with them. But in this video, we're going to look at the visual aspect. So we're going to go right by about 7 units, and then we're going to go up 1, 2, 3, 4, 5. And I'm going to put an initial point right here, and then I'm going to put a terminal point right here. So we could even write that. The initial point is where you start. Of course, direction does matter, so that'll be important. And then the terminal point is where you end. So that'll be right here. And we usually indicate that at the terminal point by an arrowhead. This is kind of similar to a ray, but a vector is a little bit different. Again, with a vector we are talking about direction and also magnitude. I'm going to name this vector. Let's name this vector R. And the convention is when you name one of these things, to write it down, you put a little symbol that almost looks like a ray, but it only has one little barb on the top. So it's important that we differentiate between an arrowhead all the way across here, and which is what you would see here, but here we don't. We just see half of an arrowhead. So you would say this as vector R. Let's draw one more vector. We're going to compare these two things here. So let's draw another one. In this case, let's have our initial point at -2, -3. But we're still going to go 1, 2, 3, 4, 5, 6, 7 left, and 1, 2, 3, 4, 5 down. We can draw an arrowhead. Again, this would be our initial point and our terminal point. And just for grins, let's name this S. And then remember, our vector sign is just kind of like a half of an arrow, I guess you would say, or just a one barb one. Now, vector R here is drawn in standard position, so we can write that maybe off here on the side. Whenever a vector, whenever the initial point begins at the origin, the terminal point can be wherever you'd like, but the initial point here has got to be at the origin. When that's the fact, that is going to be in standard position. Notice that S is not in standard position. We could move it, we can just pick it up and kind of move it. And so oftentimes we do that. We take that vector and try to write it in standard position. Now what we're going to do is we're going to take a look at some of these things down here. So I'll go ahead and move this up just a bit. And we want to know our vectors R and S equal. Well, for two vectors to be equal, there's something very specific that we need to know. And so with equality of vectors, they need to be same direction. So we'll write that here, same direction, and same magnitude. And we can see here that although they look like they have the same magnitude, which is, you got to equate that to the distance here, they're not in the same direction. So we would say no. Vectors R and S are not equal. Opposite would mean 180 degrees from each other, and same mag. And that is the case. These two vectors are directly opposite of each other, at least in their direction, and then they're also, the magnitude is the same, and that needs to be the case. If they're different magnitudes, we don't say that they're opposite. So we would write yes for this one. For parallel, parallel vectors will be either same or 180 degrees from each other direction, and magnitude doesn't matter. And we would say that these are definitely parallel. And you could imagine that if you took, you know, this vector here and extended it on an imaginary line, and this one here and extended it on an imaginary line, of course that's not the actual vector itself, but you could see that their directions are exactly opposite of each other, and the magnitude here doesn't matter. We can say that the vectors are parallel. So we can write a big yes right over here.